Hi, I have a question for you. What is the device that you think you interact the most when you're using your computer or laptop? Probably you answer the keyboard, right? So this is the device that we use every day to interact with our computer. And if you look at the letters, how they are placed on the keyboard, you realize that they are not following the alphabetic order. Probably they start with Q, then W, E, or if you are in France, they may start with A, but it's not the alphabetic order. So you may be wondering, why is that so? And the reason is probably the way they are placed is more efficient. When you're moving your hand on the keyboard, you will be faster if they are placed like that. Now the question is this the best way to place the keyboard? Is there any other more efficient way? Well, actually there was, and that was called the Dvorak. And the Dvorak keyboard was better, but nobody is using that. Why? Because people were so used to the one we have right now that switching to the Dvorak keyboard would have been difficult. Because people, they like routine. If they are used to something, they keep doing that. And the switching cost is a barrier to move to another technology. Same way when you are going from your house to a park and you're used to taking that path, that route, you keep doing that. Even though someone tell you that, hey, there is a fastest way, maybe you don't care because you are so used to the one you took every day. So why am I talking about keyboards? My name is Alberto. I am a researcher in the field of optimization, and I face these kind of problems very often. Not problems with the keyboard, but problems of developing something that may be better than existing methods, and yet people are not using that. So let me explain. If you're not familiar with research, in academia especially, what happens is that you need to publish articles, submit to journals, so that's what you do. But the language that you have to use to publish in those journals is usually very complex. So if I have a good idea and I develop something and I want to write a paper about that, great. But I have to write in a way that is hard to understand. I don't want to go to the details of that. This will be the topic for another video. But let's just say that a non-expert taking your paper will have really a hard time to understand what you have done. If someone from industry, for example, got a problem that my methodology that I develop in my article could solve very efficiently, well, if I go there and I give them the paper, guess what happened? They will not use it. Why? Same reason as the keyboard I mentioned at the beginning. Because they are so used to what they are doing that even if there is a potential benefit, the switching cost will be too much. And let me show you what I mean. This is an example, the paper I wrote, and is also the topic of this project. Is about network interdiction, and soon I will tell you what the problem is. But let's just say you don't know anything about optimization and coding, and I say, hey, this is the solution for your problem. You just need to go through that, and you start to read, and you start to find equations, and then optimization problems, and then proof and theorems, and then you see even okay, I have the pseudocode here, but if you're not an expert, what do you think will happen? Exactly. You will say, thank you, you put this article aside and you keep doing what you've been doing in the past. So with this project, I want to propose a way to at least reduce this gap. The gap between the research that is done in academia and the potential application in industry, for example. And how to do that using generative AI. The project is called N.I.R.A.D, and it means, if we go down, Network Interdiction Resilience Advanced Defense. So what is network interdiction first? is what I show you in that paper, but the main point, just to make it simple, imagine you are looking at a metro system. So in your metro, you have the stations and you have the links connecting the stations. And now imagine that there is an attacker, the bad guy, who wants to destroy some of these links between stations. And his objective is to disrupt the system, to push the flow of people to low values. Now, if you are the system operator and you have a budget to fortify your links, that means I can invest some money in a link so the attacker needs to pay more money to destroy that. Well, the question you may have is, how do I allocate my protection resources, my protection budget to those links the best possible way? The best possible way means I want to make the system as resilient as possible. That means I want the enemy to pay as much as possible if he really wants to destroy the system. Now, this is the question that we address in that paper, but again, if I tell you that I have a methodology to do that very efficiently, and that the solution you find is the best you can find, but then you have to go through all these, you may not want to try. So with this system, my idea was, given that I have all these methodologies in the paper and I have the Python code of that, what if I make them accessible with agents and generative AI? And that's exactly what we did in this project. This is the blog post where you can find the explanation of how it works, but for the time being, let me go through this submission that I had on Kaggle. Is the submission for the competition of this generative AI intensive course capstone by Google. That was a great way to learn how to use generative AI in context like this one. And then I want to show you more or less what is the idea. So the problem we have facing is the one I just explained, network interdiction. We have a research paper, it's very hard to understand. Let's code everything and make it accessible to non-experts. And to do that, we use agents, okay? So agents are those tools that we can code, and we can give these tools to an LLM, in this case, the Gemini LLM, and therefore, when we ask a question, the system will not hallucinate, it will not invent, but it will run the specific function that we code in order to give us the solution. So the user doesn't need to know the details or going through the paper, no. He just needs to know at a high level what our software can do and what is the kind of questions that he can answer. And that's it. And then he can ask questions in natural language. So I want to show you a few points that I think are interesting here. This is the kind of system that we are looking at. Is a simplified network, okay? And then we are sending from the red node to the green node some commodity. Like in a network system, the metro I mentioned at the beginning, it can be people, right? Flow of people. So we want to send as much flow from the red to the green through these arcs. And you see two numbers in the arcs. The first number is the capacity. How much can I send? And the second one is a cost. How much is an attacker going to pay if he wants to destroy this arc? That means to send the capacity to 0. And here we load the data. And the first feature that I want to mention that was great in this project is that often we have to prepare data. In this case, it's a simple text file. But what if I have this picture and I want LLM to transform that into the right kind of data? Well, that's possible. And this is one of the features that we use in this project. This is the data that we loaded from the text file. And then by creating the appropriate prompt and then calling an LLM and explaining the kind of output that we want, we gave that picture as input and we were able to get the same data. So this is a first thing that can be really interesting when people can save time instead of writing down everything, if they have a picture of what they want as a network, it can work. Of course, if the system is very complex, it may be impractical, but still I think it's great. And then what we did, we defined the optimization problems here. So this is the Python code associated with the paper if you want. And then we define the tools. So the tools are those kind of functions that we can give to the LLM, and we can give capabilities to the LLM to perform the associated actions. So we can somehow control what LLM can use. And here there is a bunch of them. And this one here, compute resilience, is implementing basically the pseudocode you have seen in the paper, right? So you don't need to go through that and understand all the details, but that's what is happening, right? Is finding the best allocation of our fortification budget to make the system more resilient. Then we create an agent, we give this prompt explaining what it should do, some examples of the kind of answer that we expect, and then we say, look, these are your tools, this is what you can do, and that's it. And then we test it. So we started to ask questions to this agent about the network. For example, one question here was, what is the max flow? What is the maximum I can send? And then the answer is, well, the flow is 9, and then it's telling me how much I have to send through each arc. Now, next question is, what will be the worst case attack if the attacker has a budget of 3? And then again, it's telling me what is the arc that will be destroyed and what will be the corresponding flow. So we move from 9 to 3. It's a big drop. Now, I ask, what is the resilience now if my fortification budget is 10 million, so I can allocate 10 million to the different arcs, and I want to guarantee a flow of at least 6 in the worst case. And then it's telling me that the resilience is 8.7, and this is the optimal allocation of my budget. So what does it mean, 8.7? It means that if the enemy got a budget 0 to 8.7, and I fortify these arcs this way, so I put 4.2 million on the arc 4.3 and 5.8 on the arc 3.5. So the new costs are these. This is the updated cost. You see that here we increased to 8.8 and here to 5.3. Now in this new situation, whatever the enemy can do, costing 0 to 8.7, and I can always guarantee a flow of 6. And in what we did here, we ask a question, okay, now with this new system, what will be the worst case attack if the budget is 8.7? And then the answer is 6. So if it's more than 8.7, we try to ask 8.8, then you see that we go to 3. So it's correct, right? And the good thing about this method is that 8.7 is the maximum you can achieve given your 10 million budget and your flow requirement of 6. Now, if you have a situation like that in real life, of course it may be slightly more complex, but people may not be using methods that give you the best solution. Maybe they get something that doesn't provide this 8.7, maybe they can get to 6 or 7, whatever. So they may not have the best way to allocate the budget. And again, if I go to them with a paper, they may still be using that. But if I speak their language, and now everyone is used to GPT and to LLM, if I give them access to a tool like that, then I guess they are more likely to use it. So I also created here a interactive interface. It's commented, but what happens here is that you have the question, the input box where you can input your question, and then the system will answer, and then you can ask new questions. And when you are done, you type exit. I don't run it here, but feel free to run when you try this. And of course, this sounds great, right? We have agent that can do that, and then we have a system that is able to answer. And then here I also did the concatenation of the prompts, so there is somehow the memory of what I've asked before. And then it's like, okay, it's great. It's even too good to be true. What's the catch? Well, This is not perfect. Why is not perfect? Because even in this kind of situations, the LLM can still do something wrong. During the test sometimes, and I was able to mitigate through the prompt much of it, but it can still happen that you get wrong computation. Mostly because the way LLM is interpreting your question and generating the data for the function may be somehow wrong. It's very unlikely, but it can happen. An example was the understanding of the picture. So when I was using the LLM, the Flash, Gemini 2 Flash, it didn't understand for some reason one arc. It was still wrong. And I tried different prompts and it didn't work. But then I switched to another one, another Gemini LLM, and then it was correct. But you need to check, right? It's very important when you use this system to check, and there is a way that I explain here where you can have the printed reasoning sequence. So you can check if what is going on is correct or not. But I still think that is a great way to make research more accessible. So again, I want to stress it that the potential is great, in my opinion. Is a very effective way to reduce the gap between research, academic and theoretical, to something more concrete that can have an impact. And given that the LLMs and the AI capabilities is improving day by day, I think this can only become better. On the other hand, I want also to recall that it's not perfect. It's not the solution to every problem. You still need to know what you are doing and to double check. And this reminds me something, by the way. There was this story about these two engineers, and there is one of them who was designing a system to prevent people for typing weird combination of input for a form, right? So imagine you go online and you have this form asking you insert your name, but you cannot use numbers, you cannot use weird symbols, and so on. And he wanted to design the best way to catch all these illegal input, right? And then he told his colleague, look, I think I got it. You can try to input every possible string you want. If it's not following the rules, the system will block it. And then the guy started to say, okay, let me try. And then he tried to put some illegal input, and then the system catch it. And then he was, okay, it seems it's working. Then he tried to put something more complex, and again, the system was working. So his colleague was like, you see, I did it, it's working. You can write, everything is perfect. And then the guy say, oh, really? Okay, let me try that. What if I press everything? What if I press all the buttons in the keyboard at the same time? And then his colleague was, what do you mean? And the colleague say, well, what I mean is that I take this keyboard, right? And then I just smash it on the table and see what happens.